Welcome to the next lecture. We will continue our discussion with digital modulation techniques. Last lecture we ended up with quadrature phase shift keying or quadri phase shift keying, that is Qpsk. I will again briefly recap that. So in Qpsk, your signal, the pass band signal, that is the signal which we will be transmitted, is represented as Si of t under root of 2e by t cos of 2 pi fct plus 2i minus 1 pi by 4 for 0 less than equal to t less than equal to capital T and I is equal to 1 2 3 4. So this can be expanded as, we will use cos of a plus b, that is cos a cos b minus sin a sin b. So under root of 2e by t cos of 2i minus 1 pi by 4 cos of 2 pi fct minus root 2e by t sine of 2i minus 1 pi by 4 sine of 2 pi fct. Okay, and then we gave a notion of, so we can basically write it as, so if we see that we can view it as we have two carriers. So let's define phi 1 of t as root over 2 by t cos of 2 pi fct, this is one carrier for one part, and phi 2 of t as 2 over t sine of 2 pi fct as another carrier. Of course, for this also 0 less than equal to t less than equal to capital T. Okay, and then we defined the notion of orthonormality. We observed that integral 0 to t phi 1 of t phi 2 of t dt, this is 0, and integral 0 to t phi I square of t dt, this is 1 for both I is equal to 1 and 2. Okay, it means they are orthogonal to each other, and also they have unit norm, that is their energy is 1. So they form orthonormal basis functions, we call it, like a basis vectors. We have basis vectors, right? I, j, k. Similarly, we have basis functions. Okay, so basis vector means that given any so given I, j, k, we can represent any vector 3i plus 4k plus 6j. So any vector can be represented in terms of I, j, k. Similarly, basis function means any other function can be represented in terms of these two functions. Okay, that is what basis function means. So in particular, we can then rewrite this as I of t as under root of e cos of 2i minus 1 pi by 4 phi 1 of t minus root of e sine of 2i minus 1 pi by 4 phi 2 of t. So we can treat them phi 1 phi 2 as equivalent to unit vectors. So then what are the components? So the components are root e cos of 2i minus 1 pi by 4. Okay, and the other component is root e sine of minus root e sine of 2i minus 1 pi by 4. So this forms a vector. This is how we can say. Okay, for I is equal to 1 2 3 4, and I can call it Si vector, right? Actually it has two components, so I can say Si1 is root e cos of 2i minus pi by 4, Si2 is minus root e sine of 2i minus 1 pi by 4. So it has two components. Okay, and now if we give different values, suppose I will give I is equal to 1, so I will get s11 equal to root e by 2, because cos of pi by 4 is 1 by root 2. Similarly, s12 will be minus root e by 2. So like that you can give I is equal to 2, you will get s21 equals minus root e by 2, and s22 will be equal to plus root e by 2. So you can give I is equal to 3, you will get s31 equal to minus root e by 2, and s32 equal to minus root e by 2. Okay, similarly I is equal to 4, we will get s41 equal to root e by 2, and s42 equal to minus root e by 2. So we form different vectors, so like this. So you will form one vector will be root e by 2 minus root e by 2. Oh sorry, this will be plus the first one. Similarly root e by 2 minus root e by 2 and minus root e by 2 root e by 2 root e by 2 minus root e by 2, like that. So we can represent them in two-dimensional axes like this. So if this is root e by 2, this is also root e by 2, this is minus root e by 2, this is minus root e by 2, and this is phi 1 axis, this is phi 2 axis. So then this is one point, other point, other point, and other point. So as explained yesterday also, they can be assigned, a particular bit. Suppose I can represent it by 1 1, then 0 1 0 0 1 0. By assigning binary numbers in this way, we ensure that when we move from one point to other point, the only one bit changes. It's called gray coding. Okay, so far so good. Now we will today see that how to represent Qpsk waveform. Okay, Qpsk waveform. So let's suppose that we have done sampling. So this is the step. Then we have done quantization, then pulse code modulation, and now we have some binary sequence we transmitted. Now let's suppose the binary sequence is 0 1 1 0 1 0 0 0. Suppose this is one part of the sequence which we want to transmit. So what is done is this sequence is divided into two parts. One, the odd numbered bits, and the even numbered bits. Okay, so we will start it like this. So 0 1 1 0, then 1 0 0 0. The two bits are paired actually, and they are called die bit also. Okay, so this is die bit 0 1, this is die bit 1 0, similarly 1 0 0 0. This is the input binary sequence. Now if you start from this indexing, this is 1, position number 2 3 4 5 6 7 and 8. Now what is the odd numbered, what is the odd position sequence? So bits at position 1 3 5 and 7. So bit at position 1 is 0, then at position 3 is 1, then at position 5 is again 1, then at position 7 is 0. Okay, Now you remember the nomenclature. So Si1, this is representing the first part. Okay, let me go back here like this. Si1, this represents the cos part. Si2 represents the even part. So in fact I can also write Si of t as Si1 phi1 of t plus Si2 phi2 of t. This is another way of representing the QPSK signal. I will repeat here once more because some of you are completely new to this. Just compare it with a vector A. Suppose in 2 dimensions you have A1I plus B1J, right? So this I and J are unit vectors. Equivalent to this we have orthonormal functions. These are called basis vectors. These are called basis functions. And A1, B1 are the coordinates. So we have here Si1, Si2. They are the coordinates in phi1, phi2 axis. Okay. Now what we do is the odd part of these bits, the odd bits, they are represented by Si1, the first part, and even bits are coded by the second part. Okay. So now I will on this axis here I will plot Si1 phi1 of t. Just remember phi1 of t. What is phi1 of t? I will recall phi1 of t is the cos signal 2 over t cos of 2 pi fct, right? Now here it is 0. You know that 0 is represented by minus root e by 2. So I will write here minus simple. 1 is represented by plus. This is represented by plus. This by minus, right? Now minus means, see, it is cos. It should actually start from this point, but because it is 0, so minus means it will start from this point like this. Okay, and end it here. Now after this you have 1, so 1 will start from this, and this time period is t. Okay, it is t. Now so again it will continue because it is 1. Here, then from this point it is 0, so 0 will start from minus again. Okay, so this is how odd bits will be encoded. Now even numbered sequence, first of all, what are the even bits? The bit number 2 1, bit number 4 0, right? Then bit number 6 again 0, bit number 8 0. Okay, what I mean is, go back here, this is bit number 2, bit number 4, bit number 6, bit number 8. These are the even bits. So it is plus minus minus minus. But now what is so we will plot its waveform on this axis, and even bits are represented by second part, that is Si2 phi2 of t. I will take back to that. There should not be any confusion in this. So look at this equation back. Si of t is Si1 phi1 of t plus Si2 phi2 of t, where Si1 is root e cos and Si2 is minus root e sine term, and the first term is modulated by phi1 of t, the second by phi2 of t. So the second part will be used to transmit even bits. Okay, even numbered bits. That is what I mean. Now since it is sine will start from 0, so like this. So we have This completes the period. Then there is a change in sign, so it is 0. So it will start like this because minus. Then it will be continue because there will not be any phase change because they are all zeros. Okay, and this is your time interval t, right? And then what will be Si of t? Si of t is Si1 phi1 of t plus Si2 phi2 of t. So you have to add them up. So if you add them up, okay, so the overall signal will look like this. See, the phase change in the parts was pi by 4, but the phase change when we add them up is, sorry, was pi by 2, but phase change in overall signal whenever there is a change in sign is not pi by 2, it is pi by 4, multiple of pi by 4, maybe 3 pi by 4 or whatever. So this is the overall signal, Qpsk waveform. Now this particular example prepares us for the modulator design of Qpsk signal. So it will be, now you can think of Qpsk as two BPSK signals. This part looks like BPSK, as I told last time. This part also looks like BPSK. So here is now Qpsk transmitter or modulator. So Qpsk modulator or transmitter. Okay, now see, I am omitting those steps. What steps? So you actually have analog signal, you may have analog signal, then you do the sampling, then you may do quantization. By the way, quantization is actually analog to digital conversion, okay? And then you do PCM. So these all things, so we have binary sequence. So we start from as if we have binary sequence. There is a reason for it. One reason is that in some cases, especially in data communication, suppose you communicate, you're on WhatsApp or the computer, that directly comes in the form of zeros and ones. So there is no need of sampling and other things. Sampling is needed in case of audio and video signals. Anyways, so we have now binary data sequence. Okay. Then definitely we have to first do line coding. We have to represent bits by plus minus signal. So we have polar, non-return to 0, level encoder, same as BPSK. Then we have one important step which is different, that is demultiplexing. What will demultiplexer do? It will divide the incoming bits or incoming signal into two parts. So here we need two parts. One I will represent by A1 of t. This is the odd bits part, and the other I will represent by A2 of t. This is the even bit part. Okay. Then this odd bit part you will modulate using the cos signal, cos carrier, and the even bit part we will modulate using phi 2 of t. Okay, and then definitely we have to add them up. So we will need an adder, and here is our Qpsk signal which can be transmitted over the antenna. Okay, now it immediately tells us Qpsk demodulator also, that will also demodulator or receiver, that will also be almost that will have the same steps as in so BPSK, except the last setup where we have to combine the bits. Now see, let the received signal which you receive from the receiver antenna, let that be represented by x of t. Okay, So now what we will do, we will multiply this x of t separately. First we will multiply it with phi 1 of t, then we will multiply it with phi 2 of t. Okay, okay, let me now explain first what happens with multiplication. So I will represent this s of t is s, let me see, it's si of t, si1 phi 1 of t plus si2 phi 2 of t. Okay, where si1 is that cos of pi by 4 i2 i minus 1, and si2 is sine of pi by 4. Phi 1 and phi 2 are the, these are our carriers, orthonormal pair also. Okay, so now what will be si of t phi 1 of t, and that too integrated over 0 to t dt. So what will you get? 0 to t si1 phi 1 of t plus si2 phi 2 of t dt. After simplification we will get this one. Okay, phi 1 gets multiplied to both the terms, si1 si2 do not depend on time, they will come out of the integral. Now phi 1 phi 2 forms the orthonormal pair, so integral phi 1 phi 2 dt will be 0, right? And integral phi 1 square will be 1 because they are of unit energy, so I get si1. Now if si1 is greater than 0, then we declare that this part of bit, which is the odd bit, that is binary 1, right? And if it is less than 0, we declare it is binary 0. Similarly, 0 to t si of t phi 2 of t dt, you do the analysis the same way, that will be si2, second part of the bit. So that again, if it is greater than 0, we declare it is binary 1, if less than 0, we declare it is binary 0, right? So what should be here after this? As in BPSK, we will have an integrator which will perform this step. After integrator, we will get, I will write here x1, although I am taking right now noiseless case because this part of the class is common for BTech and MTech. I don't want to annoy BTech people with noisy cases. But after this, I will have a separate video for only postgraduate people where I will take the Gaussian noise into account. Right now, we will take noiseless case. So x of t is directly equal to si of t. Okay, so this x1 actually here is equal to si1. So I need a decision device here, which should actually see the sign, compare the x1 with threshold, which is here 0, right? And output it should give whether it is, if it is 1 it will emit 1, if it is 0, if this bit is 0, it will emit 0. Similarly, same integrator here, I will get x2, I will have a decision device which will be fed with threshold, and then I need to combine these two bits. So see, the upper one will be odd bit decision, the lower one will be for even bit decision. So I need a multiplexer, and then this is the we have here the binary sequence which was transmitted. So this is the Qpsk modulator and demodulator design. Okay, so it is similar to BPSK. That is why I told you at one point that if you understand BPSK, then understanding Qpsk is not a big deal. Now I will, this is the proper time to introduce one more modulation scheme which is almost similar, that is called M-ary phase shift keying, M-ary PSK. So what is M-ary phase shift keying? Actually you will see later on that Qpsk BPSK will become special case of this. In M-ary I say that the signal Si of t, as it was represented in case of Qpsk also, so 2 pi fct plus, in Qpsk I wrote pi by 4, So here we say y pi by 4, I will write 2 pi by m times I minus 1. And I take m I is equal to 1, 2 up to m. M is any multiple of 2, a power of 2, sorry. So there is a why we should have m power of 2, because we are going to represent binary numbers with it. So we cannot have 7 waveforms, because log 7 to the base 2 is not a proper integer. Okay, so we need m to be power of 2. So E is the energy of the signal per symbol, and the carrier frequency Fc is Nc by T. So as an example, if I take m is equal to 8, so how will this signal look like? Cos of 2 pi fct plus, it will here become, since m is 8, it will become pi by 4 times I minus 1, and I is equal to 1, 2 up to 8, right? Now you can see that if you give I is equal to 1, so S1 of t will be 2e by t cos of 2 pi fct plus, so if you give I is equal to 1, the phase is 0, right? If you give I is equal to 2, so S2 of t cos of 2 pi fct. So if you give I is equal to 2, it becomes pi by 2, right? So in particular, if I will write there I and this phase pi by 4 into I minus 1, so I is equal to 1, it becomes 0. I is equal to 2, it becomes pi by 2. I is equal to 3, it becomes, so sorry, for I is equal to 2, it will become pi by 4, sorry. So for I is equal to 3, it will become pi by 2. I is equal to 4, it will become 3 pi by 4, and if I is equal to 5, it will become pi. I is equal to 6, it will become 5 pi by 4. I is equal to 7, it will become 6 pi by 4, which is 3 pi by 2, and I is equal to 8. Finally it will become 2 pi. Now to get its more clear vision, so as we did in Qpsk signal, we'll expand it, cos of a plus b formula. So Si of t, which we had written as 2e by t cos of 2 pi fct plus pi by 4 I. So let me write first for general M-PSK. So it is 2 pi by m I minus 1. Okay, so first of all, if you look here, if you put m is equal to 4, you will get Qpsk basically, because you will get 4 signals. Now this we can use cos of a plus b, so under root of 2e by t cos of 2 pi fct cos of 2 pi by m I minus 1 minus root 2e by t sine of 2 pi fct sine of 2 pi by m I minus 1. So again, same story, you can write it as root e cos of 2 pi by m I minus 1 phi 1 of t minus root e sine of 2 pi by m I minus 1 phi 2 of t, right? And this further can be written as si1 times phi 1 of t plus si2 of phi 2 of t. Okay, now you, so for m is equal to 8, this si1, it becomes cos of pi by 4 I minus 1, and si2 root e, it becomes minus root e sine of pi by 4 I minus 1. Now again you have phi 1 phi 2 axis, but now you have 8 points, right? So if you will put I is equal to 1, so this S11 will become, so it is I is equal to 1, cos of 0 is 1, so it becomes root E, right? And Si2 will become I is equal to 1, it becomes 0, right? Similarly you put I is equal to 2, so S21 will become, so cos of pi by so it is 2 pi by 4, so root E by 2, and S22 will become sine of pi by 2, so minus root E by 2. Similarly you do it for I is equal to 3, so S31 becomes, so cos of pi by 2 which is 0, S32 will become sine of pi by 2 which is 1, so it is minus root E. Okay, so like that you will get several coordinates. So one is root E0, so that is here. The other you will get at pi by 4 phase, here it will be root E by 2, root E by 2. The other one you will get here, that will be 0 comma root E. The other one you will get here, that will be root E by 2 minus root E by 2. The other one you will get here, that is again 0 no minus root E comma 0. Other one you will get here, that will be minus root E by 2 minus root E by 2. The other one you will get here, that will be 0 comma minus root E. The other one you will get here, root E by 2 minus root E by 2. So it forms sort of a, they lie on a circle with radius root E. Okay, so you have now 8 points. So we know that 2 to the power 3 is 8, so each point can represent 3 bits. Suppose if I start from this 0 0 0, it's up to me what bits you can any point can represent. The next one I can represent as 0 0 1. I will go for gray coding. So next I can represent as 0 1 1, right? The next as 0 1 0. Just see, I'm doing gray coding, only one bit is changing. The next I can write as 1 1 0, right? Then next I can write as 1 0 1, and next I can write as 1 0 0, and next one sequence will be, oh, I think I'm in trouble here, because so here is 0 0 0, it should be here something like 1 0 1. Okay, so 1 0 1 to this point I can have actually 1 1 1. I think this works fine, but then no. Okay, I think if I put here 1 1 1 and then here 1 1 0 1, and then yes, now it works fine. See, this is gray coding, because if there is only one bit change in the two consecutive points, there are less chance of errors. Okay, so only one bit change, only one bit change, and this is how it is done. So we are able to transmit 3 bits with a single waveform. So definitely if you chose time period 2 same as the time period you chose for BPSK, then definitely you are having 3 times data rate. Okay, so this is the another one M-PSK modulation. Okay, so there is one more important, one more modulation scheme left, which is the quadrature amplitude modulation, that I will show you separately. But now it is a time for introducing the noise in the system and doing the performance analysis in presence of noise. That will be our next topic.